name is Joel Denny. I work at Oak Ridge National Lab, and I will be talking about the Clacc project. First, I want to acknowledge the Exascale Computing Project, or ECP, ORNL's Experimental Computing Laboratory, and the Oak Ridge Leadership Computing Facility for their support. In case you're not familiar with it, or maybe you've just forgotten, I'll start off by briefly explaining what Clacc is, and then I'll give an update on recent activity after that. So Clacc is a project that has been funded by ECP to develop OpenACC support for C and C++ as an extension of Clang and LLVM. A key design decision we made at the beginning of the Clacc project is to translate OpenACC to OpenMP in order to build on the OpenMP support being developed by a number of different organizations. This slide shows the URLs for Clacc's ORNL homepage and for Clacc's source code, which is hosted publicly on GitHub. I am the primary developer and contact person for Clacc. I mentioned that the Clacc compiler translates OpenACC to OpenMP, so I want to clarify what that means for Clacc users. There are two compilation modes. The most important mode is traditional compilation mode, which compiles OpenACC to a binary similar to any traditional OpenACC compiler, such as NVHPC or GCC. However, under the hood, Clacc first translates OpenACC to OpenMP, which thus serves as an intermediate representation that does not need to be exposed to the Clacc user, but that enables Clacc to maximize its reuse of the OpenMP implementation. Because Clacc translates OpenACC to OpenMP for the sake of traditional compilation, it seems reasonable to expose the OpenMP source to users who want it, and this is the goal of source-to-source mode. In either mode, a challenge is that there are some OpenACC features that cannot be represented in OpenMP. Clacc's solution has been to devise OpenMP extensions as the need arises. For example, we have previously contributed Clacc support for dual reference counters to upstream Clang and LLVM's OpenMP support. So that's a reminder of what Clacc is all about. Now, what is the current status of Clacc's OpenACC support? Clacc supports OpenACC's most critical features, including many directives, runtime library routines, environment variables, and the OpenACC profiling interface, which has been successfully integrated with Tau. Clacc is still missing some notable features. For example, it does not yet support the kernel's construct, and async wait support is still under development. Since the beginning of the Clacc project, Clacc has supported C as a base language, and we have recently made significant progress on C++ support, which I'll talk more about in the next slide. Clacc is regularly tested on x86-64, Power 9, NVIDIA GPUs, and AMD GPUs. And we have taken care to make it straightforward to integrate support for new offload architectures as they are added to upstream Clang and LLVM's OpenMP support. For example, we look forward to one day adding Intel GPU support when that lands upstream. We have per commit and nightly CI testing set up to run on ORNL's Excel cluster and OLCF's Ascent system. Our CI setup includes testing with the University of Delaware's OpenACC V&V suite and with Kokkos' OpenACC backend. Additionally, the University of Oregon has set up nightly CI testing of Clacc as part of the E4S project under ECP. I also want to point out that the Clacc project has been beneficial for more than just developing an OpenACC implementation for Clang. We have actively participated in the OpenACC technical committee, contributing improvements to the OpenACC specification. We have also contributed various improvements to upstream LLVM, including improvements to Clang, OpenMP support, and LLVM's testing infrastructure. The expectation is that in the future, Clacc's OpenACC runtime work will benefit Flang's OpenACC support for Fortran. Now, I understand that this slide probably doesn't answer every question you might have about Clacc's current OpenACC support. If you would like a detailed description, the top-level README and Clacc's GitHub repository points to Clacc's status and design documents. If you would like to see some evidence that Clacc can support real OpenACC usage, I'll address that in the next few slides. You might have heard of the KokkACC project, which has developed an OpenACC backend for Kokkos. The KokkACC team is from ORNL. It includes Pedro Valera-Lara, Sam Lee, Mark Gonzalez-Delata, Jeffrey Better, and recently Keita Teranishi. KokkACC won the Best Paper Award at the WACCPD workshop located at SC22. This paper showed that the OpenACC backend compiled with NVHPC can sometimes outperform Kokkos' CUDA and OpenMP target backends. KokkACC is not just an ORNL internal project. Its OpenACC backend and Kokkos is actually publicly available in upstream Kokkos' developed branch. The KokkACC project has driven C++ support in Clacc. Clacc can fully compile Kokkos with the OpenACC backend and correctly run the KokkACC team's example applications, even though they were originally developed for use with NVHPC. We are actively working on improving performance of the Kokkos OpenACC backend when compiled with Clacc. While you won't always see great performance using what's publicly available now, we expect to soon push patches that will make performance competitive with either the OpenACC backend compiled by NVHPC when targeting NVIDIA GPUs, or the HIP backend when targeting AMD GPUs. We also plan to develop a paper explaining our work and detailing the performance results. One other interesting thing to come out of this effort is related improvements to the OpenACC specification, including a new feature that specifies implicit routine directives for C++ lambdas, automatically computed by the compiler based on the contents of the lambdas. This feature is important for performance in Kokkos' OpenACC backend. It is fully supported by Clacc now, and we expect these improvements to appear in the next release of the OpenACC specification. There are still some rough edges to Clacc's OpenACC support for C++, but I think the KokkACC case demonstrates that C++ support in Clacc is already quite far along, and that in general, Clacc can support real OpenACC use cases. While I don't have specific performance numbers to show you today for KokkACC support, I do want to show you some other performance numbers using Clacc. Throughout Clacc's development, I have frequently presented SpecXL benchmarks as sort of a checkup on the status of Clacc performance. When I did so, I usually commented that even though we've been keeping an eye on performance, Clacc development was instead focused on correct behavior and a correct mapping to OpenMP, and we depended on all the great work from upstream Clang and LLVM's OpenMP developers to boost our performance. However, I have also frequently pointed out how that can still leave a gap between OpenACC and OpenMP performance, and I've previously had to modify manually the OpenACC benchmarks to close this gap. For example, in each of the two figures in this slide, the initial results for OpenACC benchmarks compiled with Clacc are circled in yellow. The results for the same benchmarks, but written in OpenMP, are red. As you can see, the OpenACC benchmarks do not perform nearly as well as the OpenMP benchmarks. One reason is that OpenMP code is often written more prescriptively than OpenACC code. In particular, OpenACC code often doesn't specify levels of parallelism, putting more burden on the OpenACC compiler to achieve good performance. Another reason is that OpenACC codes that do specify levels of parallelism often specify vector parallelism, but not worker parallelism, due to the historical behavior of other OpenACC implementations. In contrast, Clacc translates vector parallelism to OpenMP's SIMD parallelism, which has historically had little effect on GPUs under Clang's OpenMP implementation. To address both of these issues, Clacc now supports multiple algorithms for implicitly adding worker parallelism to loop nests in OpenACC applications. While the algorithm that produces the best performance varies across SpecXL's OpenACC benchmarks, we have identified one algorithm that so far always produces performance that is competitive with the OpenMP benchmarks. In this slide, those results are circled in green. This is the first time we've been able to show such competitive performance when compiling SpecXL benchmarks with Clacc without manually modifying the OpenACC benchmarks to match the levels of parallelism prescribed in the OpenMP benchmarks. This algorithm for implicit worker parallelism also works well with Kokkos, and so it, or something like it, should become Clacc's default in the near future. By the way, all of these results are from ORNL's Frontier system, targeting an AMD MI250X GPU. And we have seen the same relationships on ANL's Polaris system, targeting an NVIDIA A100 GPU. So this seems like a generally useful optimization. Now, it is also deployed on ANL's Polaris, but in this case, it's located in my home directory. These deployment approaches both mean that Clacc is not officially supported by OLCF or ALCF, the facilities that maintain those systems. So please reach out to me if you have questions. It also means that the module commands for loading Clacc are not so easily discoverable, but everything you need is presented on this slide. Moreover, OLCF's documentation for Frontier now specifically mentions Clacc as the OpenACC solution for C and C++. Once you've loaded the module, the command module help Clacc will give a brief example to get you started using Clacc, and it provides contact info and pointers to more documentation. This slide also shows how you can load TAL if you'd like to use it to profile your OpenACC applications. If you want to install Clacc on another system, you can follow the typical git clone and CMake procedures, or you can use SPAC. This slide gives the name of the SPAC package, which we do not maintain ourselves, but of course we'd be happy to help or point you to the right people if you run into trouble. To get started with either approach to installing Clacc, please see Clacc's top-level README in GitHub, which gives lots of information and many examples for installation. Or just reach out to us. We'd be happy to help you install Clacc yourself, or to look into deploying Clacc on another system. So, what is the future of Clacc? I hope you agree that Clacc has come a long way under ECP. But I'll be blunt, ECP ends after December. There are possibilities for future Clacc funding, but it will likely be for much less than 1 FTE. During the Clacc project, we have tried to solicit help from other developers. Of course, by design, we inherit a lot of great code from upstream Clang, LLVM, and OpenMP developers, and we much appreciate the University of Delaware's and the University of Oregon's help with testing Clacc, and their and NVIDIA's efforts to get more people involved. However, no one but me has contributed code directly to Clacc's implementation. With Clacc's developer base about to shrink from 1 FTE to less than 1 FTE, we wonder what we can do to keep Clacc alive and not throw away all this work. Will we attract more developers if Clacc had a committed user base? Would we attract more developers if we contributed Clacc to upstream Clang and LLVM? So let's talk about Clacc's committed user base. Right now, that's KokkACC. Could we attract more users if Clacc had a committed developer base and thus could grow its capabilities faster? Could we attract more users if we contributed Clacc to upstream Clang and LLVM? So let's talk about contributing Clacc to upstream Clang and LLVM. Near the beginning of the Clacc project, we reached out to the upstream Clang and LLVM community and proposed contributing Clacc. We got a mixed reaction. Some were very negative about the idea. Some were supportive. But one point that stood out is that upstream Clang explicitly, and really all of LLVM implicitly, has a list of very reasonable criteria that must be met before any major new feature can be contributed. I've reproduced that list here on the right side of the slide, not in the same order as on the original webpage, but I'll link to that here. I think Clacc satisfies the first two criteria easily via the OpenACC specification and our involvement in the OpenACC technical committee. I'm pretty sure Clacc satisfies the next few requirements, which are focused on design, implementation, and testing. Of course, we might have to make some adjustments during upstreaming, as that's typically how upstreaming goes. But what about a long-term support plan? Clacc's bus factor has always been one. It's about to get worse. What about a significant user community? It's just KokkACC right now, and that's relatively new. So do you see the problem here? Which comes first? My thought throughout the Clacc project has been that the key to breaking this dependency cycle is a quality implementation. In other words, if Clacc can eventually compete with established implementations such as NVHPC and GCC, maybe that will attract the attention of existing OpenACC C and C++ users, and then developers, and then we can meet the criteria for upstreaming to Clang and LLVM. Well, with ECP ending, we need to find out. Let me put this another way. Please reach out if you are interested in Clacc. We need to hear from you. Thank you.